Hey, Madison, I'll wait just another minute or two to see if anyone else joins us. And if not, it's just you and me tonight.
They're on the floor.
Oh,
We're
oh,
all here.
everybody's there.
Yeah.
All
Yes, we're
right.
all here.
All right. Well, if it's just the three of you, it'll be just the three of you, or is it just three, or are there more that I just can't see?
We were working on our case study.
Join? Yeah, just for attendance. What, so you can see she knows. Well, okay.
Oh, hang on. There we go.
Wait, where's the link?
Technically, my
Don't
current
double
roommate
join.
and my freshman year roommate are also here, but they're not taking biochemistry.
I could.
So they're not going to pay attention. Okay.
Maria, do not join this link.
She's so funny.
It's feedback stuff.
I have to go on rounds though because I'm on duty, so I'll dip in a few minutes. But and then I'll come back. It won't take long.
Okay. All right. Well, I want to respect your guys' time, especially since it's three of you. And oh, there's another. Who's joining us? Oh,
Maria. I don't know.
what are you doing, Maria? Oh. All right. So Connor's here.
You're right. You're on the thing.
I've never done a Zoom where their doorbell rings every time someone joins.
What's going on with my computer?
Maria, why do you don't need to be on. I see you.
Doesn't.
No, she
really
doesn't.
doesn't.
Wait, no.
What does she mean by attendance, by the way? I wasn't.
This thing is dying. Like,
I thought.
on it. Yeah, that's what mine does.
Hi, Connor.
Is it still hold on?
Do you hear this shit? Hey, Bessie.
Google Docs still.
And that's the sound it's making.
All right. And now Maria was frozen in a crazy face. There she is.
I don't know why she's.
I'm gonna do my round now. Well, we haven't.
She said double it and give it to the.
I'll come back.
Julia, how long do you need?
You can start without me. It shouldn't be longer than like 5 minutes.
Okay.
So.
All right.
There's a snake in my boot.
All right. And I realized one of the things that I'm going to do is there's 2 slides that I needed to get through.
I'm curious.
And I have about, let me look at my slides here. So there's two, well, that's not the thing I wanted to open up where I want. There we go. So I still need to make slides on, I think, everything from membrane transport. I don't think I've made any slides yet. So I'm just counting. I have 1, 2, 3, 4, 5. Don't need to do that one. 6. So I have 6 videos that I need to make. So I get content up from that. So there's 2 slides that I needed to get done today. One of them I actually already have a video up for, and then the other one is one that I still need to make a video for. So what I think I'm going to do to sort of try to save some time here for you. I don't know why I have these in. They're not working. I think I've got my speakers on. You guys still hear me okay? Okay. I'm just going to show you the finished version of the one slide and we'll talk through it. And then I actually think I'm going to play the video from the second one, and it'll be like I'm presenting it, and then we can sort of talk about it if you have questions, but that'll get us through like the last 2 pieces of content. And then we'll sort of go into sort of the study guide piece. Does that sound okay? All right, so let me share my screen. All right, can you see the glucose transporter slide? So I know there's a lot on this slide, so I might encourage you, just listen right now. I will share out the rest of these slides after we're done here when I post the link from this. So you can have them, and essentially you'll have the complete slide deck then from Unit 7 as well, even though we just went through these last 2 pieces. So I would encourage you to maybe listen here as we go through these, this slide in particular, and then you might be able to take notes when we go through the sodium glucose transporter because I'll play that video. So understanding glucose transporters. So there's a bunch of glucose transporters. They all have the GLUT prefix, and then they have a number after them. There's like probably 8 different glucose transporters. We're not going to learn or focus on all of them. I want you to know about GLUT2 and GLUT4. All of these glucose transporters work in a passive mediated fashion. Just a reminder again, you do need to know all of these names, okay? And so when we talk about passive mediated, that means we're moving polar substances across a lipid bilayer. It needs a transporter to help with that. But since we're going downhill energetically, we're dissipating a concentration gradient. We call it passive mediated. So we don't need to put any energy in for it. Okay, so this is where we are. So we're moving things from high concentration to low. All of these glucose transporters sort of work in the same sort of fashion. And to envision how these happen, I want you to sort of envision like a protein channel that's going like this. I mean, glucose is a pretty big molecule. And so if we want to transport it, we want to like open up and bind glucose in here. And you'll notice there's a couple of things. I'm going to zoom in here. Not only do we sort of have a shape that matches glucose, but we have a couple of spots where we can have some of the OH groups form favorable intermolecular forces. So that sort of helps lock it in. Same type of thing that we talked about with the potassium channel, where we're going to have to remove water from interacting with these OH groups. That's going to be a penalty. But then once it binds into this protein, this transporter site, we form intermolecular forces that help compensate for that. So once you have glucose kind of bind in there, what's going to happen, and here you can see here, glucose binds to the protein, and we're going to initiate a conformational change. So again, you can see these potential interactions, not only shape complementarity, but we've got some interactions with those OH groups. What's going to happen with this molecule, I almost want you to think of it like a clamshell or something, where it just kind of like conformational change opens up the exit side of this transporter. So now that it sort of changes conformation and it is possible to have exit here, what again is going to happen is this molecule can let go and it'll move over to the other side. Glucose will dissociate, and then we have a conformational change that'll go back to the sort of open, and they call that, darn it, they call that the recovery. And sorry, they call that the recovery step, and that gets back to a glucose transporter that's open. So I sort of want you to envision sort of going like this as we're binding glucose, changing conformation, opening up on the other side, and then we can transport glucose. So that's sort of the mechanism for how it happens. The important piece that we're going to like introduce here and we're going to continue to sort of think about is the difference between these two glucose transporters. We've, I think, talked about them sort of superficially already. So starting sort of down here with some definitional information, GLUT2 and GLUT4 are what we call isozymes or isoforms. We've seen that term already. These are proteins or enzymes that perform the same function, but are either differentially located and or regulated. So you find them in a different space and they might be regulated differently. Now, this really is more to comes into play when we talk about enzymes that do catalysis. But what we're going to see here is that GLUT2 and GLUT4 behave differently depending on where we find them. Okay, so here's what I want you to know about GLUT2. I want you to know the location where we find these two proteins. So I'll just compare and contrast here. GLUT2 is found in your liver and your pancreas. GLUT4 is found in your skeletal muscle and adipose tissue. So I want you to know where these two are located, that they're located in different spots. I want you to remember that one of them is insulin sensitive. Okay, so the GLUT4 transporter is insulin sensitive. How this works is when you have elevated insulin levels, what's going to happen is you're going to have a little vesicle that's inside of either your skeletal muscle or your adipose tissue. It has the receptors on the surface of this vesicle. What's going to happen when there's an insulin signal is you have this vesicle go to the surface, fuses with the surface, and then you're going to display GLUT4 on the surface. And this is really key. Your muscle cells, by and large, are not effective at pulling in glucose or not able to do so with a GLUT4 transporter unless there's the insulin signal that's there. That's why insulin is sort of the key that allows your muscle cells to access glucose. Here's some statistics that I sort of want you to know. It has a fairly low Km. And if you want to remember what Km is the concentration of ligand that you need to be at to have half of your ligand binding sites be occupied. So it has a fairly low Km, which means if there's less than 5 millimolar glucose, right, it's going to pull glucose in. And that's important because we only want this to be present when there's high glucose. What state will you induce in a patient or in a person if you have an insulin insensitive GLUT4 transporter? Anybody want to guess? There's going to be a prefix in front of the word glycemia.
Hyperglycemia?
So good guess with one of the words, but that's not the right word. It's going to put you into a state of hypoglycemia. So think about this. This transporter is super sensitive. If it's there, it's always going to be pulling glucose in. Okay. So we only want it to be there when we have high insulin levels. High insulin levels are only going to be there when we have high blood sugar. So it's sort of this connected piece that you will not have this transporter there unless there's insulin, which means there's high glucose. As soon as glucose levels drop and insulin drops, you resorb this glucose transporter because otherwise it will cause hypoglycemia. It will pull in glucose when it shouldn't. Does that make sense? Okay, last little piece here, contrasting that to GLUT2. GLUT4 is insulin sensitive, so only present under high blood sugar. GLUT2 is always present. It's insulin insensitive, but for that reason, it's important that it has a high Km value. Okay. And again, Km you can think of as the affinity for the substrate, which in this case is glucose. Remember this magic number, and you guys have said it before in class, 5 millimolar. That's a magic number for glucose because we need to make sure we don't fall below 5 millimolar glucose or we are hypoglycemic. Okay, so this is really only going to be transporting glucose into the liver if you have elevated blood sugar levels. Okay, and that sort of ensures that you're not going, what are you doing here? Well, but I'm in the middle of class. Charlotte. All right, Charlotte, lay down. No Daisy though. Okay, so those are the pieces that I want you to know about glucose transporters. Passive mediated, two kinds, GLUT2, GLUT4, where they're found, what their relative KD values are, and where they are in response to sort of this 5 millimolar concentration. It's important since you have a transporter with GLUT2 that's always present that it doesn't bind glucose as tightly because you don't want to induce a state of hypoglycemia by your liver constantly pulling in. Liver's only going to pull in when you have high blood sugar. We're going to revisit this piece like 3 or 4 more times as we understand how your body maintains glucose homeostasis. So questions on this? All right. I'm going to send out, like I said, the entire slide deck, completed annotated notes. But what I'm going to do now is I'm going to go over to this video and I'm going to play this one. It's about 12 minutes, so I'll let it play through. And that way you'll get sort of the content of this slide here. So I'll just play it for a second. I'll look to you guys. Give me a thumbs up if you hear it okay, as long as it's not too glitchy or anything. So in this slide, we're going to highlight the sodium glucose transport system in the context of a 3-transport overall system that allows us to move glucose from our intestinal lumen, from our gut tube, from the food that we've eaten at a meal, ultimately into our bloodstream. And it's really important that we get as much nutrients as possible out of our gut tube into our bloodstream. So how do we do that? How do we make sure that we do and move all of that? So to highlight this, we are going to discuss 3 transporter systems that are going to be a great way to review the kinds of transport that we have, whether it's
uniport, symport, or antiports, that we're going to talk about facilitated diffusion versus primary and then secondary active transport. And then ultimately, we're going to put this together in a story to explain why we do certain things when we are talking. We had this with our cholera toxin case study. Why we have to do certain types of things to be able to rehydrate somebody. Why Diet Gatorade is really sort of a fallacy and a farce. Okay, so the sodium glucose transport system is this guy that we have right here. I'm going to label it number 2 because it's actually going to be the second guy that we talk about, but highlighting it's abbreviated SGLT, sodium GL glucose transporter. So that's why it's called SGLT. But we need to couple it with a sodium potassium ATPase. Okay, that's going to be a primary active transporter. And then we're going to have a glucose uniport that we have here. So we're going to put all 3 of these together in a story to understand what's happening. So before we do that, this is a good opportunity to kind of review what we know about your gastrointestinal tract, your GI tract. Your small intestine is a really important portion of your GI tract that allows for the absorption of nutrients. Remember, your GI tract is really just a single cell thick, and we're going to see that here. So here you have kind of your small intestine, this lumen space, that's the inside space. Remember, that gut lumen really is the outside environment, because from the start of your GI tract all the way down to the end, it's just a tube that is the outside environment connected to the outside environment. Okay, but when we sort of zoom in here, as we see that we have these folds within your small intestine that kind of create these larger surface areas here. And then we have these villi here, which these are where we have these single cells that we have here. That's the single cell of your GI tract. And so these are what we call brush border cells. Okay, and they have these little microvilli that we have here. But importantly, we talked about the importance of the integrity of this tight junction between your intestinal epithelial cells. Okay, so that's a really important piece to kind of maintaining, your gut integrity and not having what we call leaky gut. Okay, and it's important then that we have transporters that are going to direct and control what's getting across this important barrier. Okay, so we're going to talk first about this sodium potassium ATPase, and I'm just going to walk through it here, and then we'll put some words down to sort of put this together. This sodium potassium ATPase is important because it builds up a sodium ion concentration gradient. So it is going to be pumping sodium out. So we're going to have a low concentration of sodium inside. Why that's important is a higher concentration of sodium outside is then going to be able to come in, and we're going to use that dissipation of that gradient as a way to piggyback and bring in glucose on our sodium glucose transporter. And then the third step is, well, once we've packed in high concentrations of glucose inside your intestinal cells, then we're going to be able to export that to the bloodstream, and then we're going to be able to get that glucose that was from your food into your bloodstream and ultimately to your cells. Okay, so let's talk about these transporters one at a time and make sure highlight what kind of transporter is it, what kinds of transportation is it doing, and then what's the net effect of what's happening. So this first transporter here, the sodium potassium ATPase, is an antiport.
And I don't know if we've used these languages. So you'll see it, but just to highlight, there's antiport, there's symport, and there's uniport. And we're actually going to see all of these. Like the name implies, anti means going in opposite direction. Sim means going in the same direction. And then uni means you're just moving one thing. Okay, so we may not have mentioned that terminology yet. So just wanted to make sure to mention it briefly here.
It is moving two things in opposite directions. And because it's moving each of those against its concentration gradient, it's active transport. And because it's using ATP for that process and moving charged species, cationic species, it's primary active transport. So this is a primary active transporter. And this primary piece, okay, this primary piece is indicating that the cost for this, the money that we're using for this, is going to be ATP. And we are moving charged species, specifically cations. Okay, so the cost for moving things against their concentration gradient is going to be paid for by ATP. So here's the net of what we are moving then. We are going to have, so that we are going to have low concentration of sodium inside our brush border cell. So this is sort of the net effect of what's happening. And we are going to have high concentrations of potassium inside our cell. So sodium is being pumped out, potassium is being pumped in, and the net effect is we're going to have high concentrations of sodium inside, low concentration of sodium inside and high concentrations of potassium inside. Okay, and that is because we are taking and pumping sodium out. So sodium is pumped out and the potassium is pumped in. Okay, so we need ATP for this process. So we need some money, biological money for it. We're pumping sodium out, potassium in, and we are building up both of those concentration gradients. Okay, so let's move on now to our SGLT transporter. So that SGLT transporter is a symport. We are moving two things in the same direction. So it's a symport. We also can think of symports as sort of piggybacking. Okay, so this symport is a secondary active transporter. And secondary active transport differs from primary active transport is the cost of this is another ions gradient. So specifically, it's the gradient that we just built up with sodium. So secondary active transport, the money is another ions gradient. And in this case, it's going to be our sodium gradient. Okay, so the money that we have here to pay the cost is that sodium gradient that we just built up. And so secondary active transport is going to be moving uncharged species. And then specifically, it is glucose in this case. Okay, so I want you to think about what we really have here is we do have a higher concentration of glucose in that lumen space to start, but we want to make sure to pull in as much of that glucose as we can. So the goal is to have a much higher concentration of glucose inside the cell than we have in our intestinal lumen. So to start, we might have glucose concentration in our lumen being higher. I can't write arrows right now. Higher, okay? But we want to make sure that we push that glucose all the way in. So the goal is that we want to have a very high concentration of glucose in our brush border cell. Okay, so that's the goal of that secondary transport is we want to have a very high concentration of glucose inside our brush border cell. We don't want to leave glucose in our intestinal lumen. That would be a waste of the food that we ate. All right, moving on to the third piece now. Now we're going to have that glucose uniport. So it's moving just one thing, and it is facilitated diffusion. So it's moving glucose from high concentration to low. So again, this is facilitated transport. Okay, and basically we are going to use that high concentration of glucose that's in the cell, and we're going to move it out into the bloodstream. So we're going to use that high concentration of glucose that's in the cell. That was what we just built up, that high concentration of glucose that's in the cell. And we're going to basically put that out to glucose in our bloodstream. And so that is the goal. We started with glucose that was outside in our intestinal lumen. Should show it here, glucose that's outside in our intestinal lumen. The goal is to basically get it out into the bloodstream. So a couple of things to tie together with things that we've already talked about with this transporter. First is it needs sodium with it. So if we want to think about this concept of diet Gatorade, if you will, remember the purpose of Gatorade is an electrolyte replacement solution. So if we want to have sodium that we get back into our bloodstream, We need to take it in from our GI tract from things that we drank, right? So if you've got an electrolyte solution, if there is not glucose that is there, you can't piggyback those in together. So glucose is absolutely essential to get the ions out of your blood or out of your intestinal lumen and into your bloodstream. So Diet Gatorade not really doing what you think you want it to do in terms of getting electrolytes back into your bloodstream. So got to have that glucose with it in order to do so. The second thing to highlight is we did see this SGLT transporter when we talked about our cholera toxin case study. So remember how cholera.
I'll let this play, but just to highlight, we obviously haven't done our case study yet. So this may or may not have content that's related to your questions, but we'll revisit this SGLT transporter in our discussion on Friday.
Toxin works is it binds to a receptor that's on our small intestine epithelial cells. And through a cascade of events, just refreshing.
I found this on the web first. It binds.
What we really have is after we have that binding, we talked about the signaling pathway that we have, that we activate adenylate cyclase. Okay, we activate and then produce more cyclic AMP. That cyclic AMP is going to activate pKa, which is our master phosphorylator. Then we're going to ultimately upregulate the activity of that CFTR, that cystic fibrosis translocator protein, and that's going to put high levels of chloride out into the GI tract, and then that's going to have water simultaneously go with it to try to balance that that change in ion concentration there. Putting high amounts of water into your GI tract are what cause that diarrhea. Okay, so that was that CFTR transporter. We'll have a short video to kind of refresh our memory on how cholera toxin works. But ultimately, the piece that's important and related here is if you want to rehydrate that individual, and if you're going to be doing something orally, you have to make sure that we've got sort of glucose and sodium in there if we want to be pulling those ions in and maintain that electrolyte potential imbalance that was happening. Is we have to have glucose there to be able to sufficiently help with that rehydration and that electrolyte imbalance situation. Okay, so that's what we have to wrap up our discussion of our sodium glucose transport system.
All right, any questions on that? All right, what I wanted to do here was, and let me see if I can I think I can get to this from here, study guide for exam 3. Go ahead and open this. So again, exam 3 is on carbohydrates, it's on lipids, and it's on membrane transport. And I would probably say it's somewhere in the like 45 to 50% for glucose or for carbohydrates, in the 25 to 30% for lipids, and then the balance in membrane transport. So certainly a greater emphasis on unit 5, then 6, and then 7. Okay, so any questions before I sort of do what we typically do is I'm just going to go through sort of our study guide. We'll look at specifics from homework and slides. I will get out to you guys as well, sort of that same sheet that I sent out before, which basically takes the topic heading for each question and sort of lets you know what to think about for that. Julia is very excited with that. So you'll have that, so you sort of have an idea of sort of what buckets of questions you'll have. But any questions before I sort of get started here?
Are the GLUT2 and 4 transporters, are they uniports or symports?
Good question. They are uniports because they're only moving one thing. Anytime we
Okay.
want to talk about either a symport or an antiport, we have to talk about moving two things. Now, I will say, Connor, just to highlight, you asked the question, it was a great question. You asked about GLUT2 and GLUT4. Those are uniports. And let me go back. Let me see if I can find, where did I have these here? So these guys are uniports, okay? And this is a uniport here, but this is also a glucose transporter, but it's a sodium glucose transporter, so it's a symport. But anytime we just talk about any of the GLUT transporters, those are always uniports. Okay. Any other questions? All right. So structure drawings. Here are, even though there was 8 that we sort of highlighted, there's some that are like not really relevant to think about, some of the really smaller sugars. But here are 5 sugars you should know about that we've spent some time thinking about: glucose, fructose, mannose, galactose, ribose. Generally be able to think about drawing them as a Hayworth projection. You are going to have to draw a sugar. Okay. The 3 that we will see later on in the semester, but I wouldn't really worry about for right now. Ribulose is one of them, but we're not again going to see that until later. And then glyceraldehyde and dihydroxyacetone. And if you've studied anything with metabolism, those are intermediates that we see in glycolysis. We see dihydroxyacetone phosphate and we see glyceraldehyde 3-phosphate. So DHAP and GAP we see in glycolysis. We'll get to those details next semester. So don't worry about those other 3, but these are 5 that I want you to know. My huge recommendation is learn glucose and learn fructose. Okay, because you can relate glucose to mannose and galactose by understanding that they're epimers of one another. You just switch the OH. So draw glucose and then you can make it into mannose by switching the OH group on C2, make it into galactose by switching the OH on C4. Hopefully ribose is pretty straightforward because you know how to draw a phosphodiester bond. So that's the ribose sugar in a Hayworth projection. And then fructose, again, that's going to be a 5-membered ring. It's going to have CH2OH groups on both the 1 and the 5 carbons. Okay. Other things to draw, and we already talked about this, is either draw a fatty acid or some fatty acid derived molecule, whether it's a phospholipid, triglyceride, given some information. So I will tell you information about the fatty acids that you'll need to have to make certain things. So you have to remember, and it's okay because sometimes they're hard to draw. If you can't draw it with the cis double bond, I'm fine if you draw it as a trans, just to sort of keep showing that zigzags, because you're likely to draw them in a skeletal structure. But you can make sure to point to it and say, I know this is supposed to be in the cis configuration, but sometimes it's weird to draw. They almost look like little trapezoids or something when you're drawing them. So I'm okay if you draw it as trans, as long as you label it and say, I know this is cis, but this is easier to draw like that. Okay, so I guarantee those are going to be 2 things you have to draw. Just like for your last exam, you had a little dinucleotide, you had a short peptide, and I think those were the only 2 things you had to draw for the last one. Okay. Structural concepts that we have here. Again, features of sugars. You know you have a sugar if it ends in OSE. You know the empirical formula for any sugar, which is CH2O. We sort of talked about this, and I don't think I've harped on this as much as I have in the past, so I want to make sure to do it here. When we talk about our macronutrients, we already talked about proteins, and so I'm going to revisit this here. Obviously, you don't need to know this for proteins for this exam. Proteins and carbohydrates have the same calorie content, 4 calories per gram. That's a number that I want you to know. Okay, lipids are 9. So I want you to know the nutritional value for carbohydrates, the functional groups that are present there, right? It's always a carbonyl containing functional group at C1 or C2. C1 is going to be an aldehyde, C2 will be a ketone. Stereochemistry, we talked about this today when we revisited with valinomycin. Natural stereochemistry of amino acids that we see in our body is L, so sugars are D. Being able to identify if something's a ketose or an aldose sugar. Furanose versus pyranose, you're only going to see those when we have cyclic forms, because that has to do with whether you're forming a 5-membered ring with a furanose sugar, 6-membered ring for a pyranose sugar. And again, the differences between sugar epimers. So for example, glucose and mannose are epimers. We've changed the stereochemistry at 1 carbon. And then anomers have to do with once we cyclize sugar, like we can have the alpha versus the beta anomer of glucose. And that has to do with once we cyclize our sugar, what is the stereochemistry at that anomeric carbon, the carbon that used to be the carbonyl, that if we're cyclizing now is the point of connection to make our hemiacetal or hemiketal. Okay. We've already sort of mentioned some of these other pieces. So when we talk about configurational or conformational isomers, right? Configurational isomers are going to be things like epimers or anomers. Configurational isomers only interconvert by bond breakage. Conformational isomers, we convert by bond rotation. So that was really sort of the chair flipping that we did to show us why beta D glucose is probably nature's favorite sugar. So highlighting the epimers we have for glucose, C2 is mannose, C4 is galactose. An isomer of glucose. So glucose and fructose have the same chemical formula, but again, we have moved glucose is an aldose sugar, fructose is a ketose sugar. Understanding when we are making glycosidic bonds, right? We talked about all the different nucleophilic players that we could have. I might sort of go back and forth here because I can see these slides in my head, but making sure to highlight here. It's just some of the things we've already talked about, right? Here's the sugars you have to know, all the ones in greens, but I highlighted you don't need to know glyceraldehyde, dihydroxyacetone, or ribulose. Don't need to know those yet. We'll get to those later. But the other 5, I want you to know those structures or know how they're all related to glucose. We talked about stereochemistry for ring closure. Again, oh, excuse me. Pyranose, 6-membered ring, furanose, 5-membered ring. Again, look at, I mentioned this, and of course I can see it in my head, but it's much better for you guys when we see a picture here. Fructose, I should have said it wasn't the C1 carbon, it's the C2 carbon or the C5 carbon, each have that CH2OH group, but be able to draw whatever anomer of these sugars that I asked you to draw. Let's see, so we talked about conformational and configurational isomers. Cyclization. So this is the slide I was seeing in my head, but as we talked about this question here on your study guide, the different nucleophilic players for glycosidic bond formation and their contexts, right? So we talked about you could have your nucleophile be an OH from other sugars. That's how we polymerize sugars. You could have your OH be from those 3 amino acids. That's how we're going to connect proteins and sugars together, and that's called glycosylation of proteins. If it's done with an OH containing amino acid, that's called O-glycosylation because we connect the sugar at an oxygen nucleophile. And then we also have nitrogen. You know, big picture, the 2 main nucleophiles or nucleophilic atoms that we see in biochemistry are nitrogen and oxygen. So again, here we can have the nitrogen coming as part of a nitrogenous base. That's how we connect the bases to the sugars when we make nucleosides, and then we can phosphorylate them to make nucleotides. But we've got 5 nitrogen-containing amino acids, right? The ones that we know that are basic, like histidine, lysine, and arginine. And then we've got glutamine and asparagine, which are amides. We don't think of those as basic amino acids, but they still have a nitrogen that can be nucleophilic. So we can attach sugars to proteins via N-glycosylation. And we also want to remember that we've got the N-terminus that we can also sort of use as a point for sugar attachment. So we talked about a few examples of sugar decoration. And so we talked about your ABO blood groups. When you attach sugars onto proteins that are on the surfaces of your blood cells, that's how we create those antigens that cause ABO blood groups. We'll talk about what you need to know about those in a minute. And then we've mentioned hemoglobin A1C quite a lot, but that number has to do with a percentage of your hemoglobin that is decorated with glucose. Okay, and the higher the concentration of sugar you have in your blood over a 3-month period, which is again 3 to 4 months is the lifespan of a red blood cell, the higher your A1C level is going to be. So it's really hard to quote unquote cheat your A1C level. You could sort of cheat and you could have a lot of variability in your instantaneous blood glucose level, right? Maria, I'm going to put you on the spot because I know you check your blood sugar a lot, right? Your blood sugar on the daily could sort of fluctuate up and down a lot. But your A1C is really sort of a time average over 3 to 4 month period of what's your blood sugar been. All right, so that was getting into different nucleophilic players for glycosidic bonds. When we talk about these glycosidic bonds, their linkages, and that concept of fuel versus fiber, that sort of gets us to these couple of slides here. For whether it's these 2 disaccharides or these 4 polysaccharides, you're not going to have to draw these, but I do want you to know some pieces. For all sort of 6 of these things that are hooked together, I want you to know the monomers that make them up and the linkages that are there. So sucrose, for example, is glucose and fructose hooked together head to head. So this is the only one where you have to have 2 Greek letters. It's alpha beta because it's head to head. We see small numbers, so it's a 1 to 2 glycosidic bond. So you want to know sort of what those linkages are. Remembering, anytime we see an alpha linkage, that should be an indication that's a fuel molecule. Beta linkage, unless you have the enzymatic key to break it, with which by and large we don't with beta linkages, that's going to become something that's indigestible. I want you to think about it like fiber. Okay. So again, I just highlighted this already, but the monomers or linkages that we see for sucrose and lactose, those are the 2 disaccharides. And then the 4 polymers are cellulose, alpha amylose, amylopectin, and glycogen. So again, know those names, know what they're built from, know what their linkages are. And then definitionally, understand the concept and difference between what we call a reducing and a non-reducing sugar. So highlighting here, for example, sucrose is what we call a non-reducing sugar. There is no anomeric carbon that's not, in our shoelace analogy, double knotted. Every anomeric carbon is tied up in a glycosidic bond. When we have something like lactose, and you may need to, given a structure, point to things. I might show you a structure and it's like, okay, or you have to draw, well, you're not going to draw a disaccharide, but if you were to see something, label the anomeric bond, label whether it's a reducing or a non-reducing sugar, or label a reducing or a non-reducing end, right? This end of our little disaccharide is what we'd call a non-reducing end, because this sugar representing the end of this chain, it's only really a chain of 2 residues, but this end, if you will, is the non-reducing end because its anomeric carbon is tied up in a glycosidic bond. This end, if you will, is what we call a reducing end, okay? Because it is still has an anomeric carbon that's not double knotted. It's only in a hemiacetal, not glycosidically linked. Okay, so hopefully that makes sense to everybody. I know I put out a bunch of videos on carbohydrate structure when we were going through this. Here's some goal numbers that I want you to remember for carbohydrates. Fasting glucose, you'd like to be under 90 milligrams per deciliter. That is going to translate to an A1C level of less than 5%. If you consistently have fasting glucose less than 90, you're going to have an A1C that'll be under 5%. Now, one little thing I just want to highlight, just a little story. This is not anything you really need to know for your exam, but you have to be careful with A1C levels. We'll talk more about this next semester. But if you, for some reason, have a pathology that causes either higher or lower turnover of your red blood cells, it's going to artificially increase or decrease your A1C level if you don't have sort of the prototypical 3 to 4 month time frame for turnover of your red blood cells. So that's just something to think about with A1C levels, is how your red blood cell health might sort of affect your A1C levels. We'll pause there for a second. I've been doing a lot of talking. See if you guys have questions. All right. Now moving on to some lipid pieces, again, structure pieces. Know the difference between omega-3 and omega-6 fatty acids, right? Structural features, general sort of functions. I'm going to go back over here. Again, I can see all the notes in my head, but to make sure to kind of highlight with you guys a lot, we talked about structure on this slide. So you may need to, for example, draw me a triglyceride that has an omega-6 fatty acid, an omega-3 fatty acid, and a saturated fatty acid. So you need to be able to put those in and connect them to that glycerol backbone. So knowing a little bit of the details about how we draw fatty acids, right? Some features that we think about with those double bonds. They're never in the cis configuration, they're never in conjugation, and they're never before carbon 9. Okay, we always have even number of carbon atoms as well. So that's sort of that structural piece. Ketone bodies. So here was our slide on ketone bodies. You do not need to know at this point the structure of these molecules, but if you were given them, I would want you to know how they're related. So for example, acetoacetate and beta hydroxybutyrate are connected by redox chemistry. They have the same number of carbons. This third carbon toggles between an oxidized form as a ketone and then a reduced form as the alcohol there. So being able to understand that relation. Oh, excuse me. And then looking at the relationship between acetoacetate and acetone, they are related by decarboxylation chemistry. I want you to know the importance of doing decarboxylation chemistry, that you need to have a beta keto acid for easy decarboxylation. So why are ketones really important? Well, we can derive them from fat, and that's really important because we have fairly substantial reserves of fats in our bodies that we can use for fuel. But ketone bodies are hydrophilic, so they can travel places in the body, especially the brain, that other nonpolar substances can't travel. You gonna behave yourself? Lay down. Lay down.
You have like a CD player?
There's a CD player in the mudroom closet that we use for.
Use it for Daisy though? Didn't you use it with her?
No, I use an iPad with her. It's what we use when we had, it's a CD player. It's what we used when we had, well, I guess we did use it for Daisy, but we take it like to drive-in movies and stuff.
Is it back down there?
It's in the mudroom closet on the shelf. Okay. Yep. Okay, routes for lipoproteins. So that was sort of this slide. I'll come back, and if there's slides that I didn't sort of talk about here, we'll come back here. That's really sort of talking about here. So I want you to know the names of the different particles, sort of where we see them. So chylomicrons, HGL, and LDL particles. And LDL sort of come in a whole bunch of gradations from LDL. They actually have something called ILDL, intermediate density lipoprotein, and then VLDL. But the key piece is understanding what is the ticket that's on the surface? What is the protein that's on the surface? Anything that goes out to the peripheral tissues is going to be labeled with ApoB100. Anything that goes back to the liver is labeled with ApoA1. So I do want you to know those little pieces. I do also want you to know sort of this concept that when you have LDL particles that are labeled small, dense, and they have this extra little protein on them, they're actually very pro-inflammatory. You can easily have blood work done to see what your LP little a level is. And if you have elevated LP little a, you are more prone to inflammation, which actually means having elevated cholesterol is problematic. So again, we talked about statins for a little bit. Somebody who has high LP little a, even though statins won't affect your LDL level or your LDL levels. I'm sorry, statins won't affect your LP little a levels. If you know that you are prone to inflammation, you need to pay even better attention to making sure your LDL levels don't get too high. And LDL levels can be influenced by statins. Let's see here. So that was the route for lipoproteins. We just talked about statins, drugs that interfere with cholesterol biosynthesis. So this is an enzyme name that I want you to know, HMG-CoA reductase. That takes the precursor, HMG-CoA. Again, two names in orange here that I want you to know. Okay, this is the enzyme that statins work on. Now, why this has so many potential side effects for statins is since we pinch our pathway fairly early on in the cholesterol biosynthesis process, there's lots of other downstream processes that are affected. Okay, because cholesterol is used for lots of these other things. I do want you to know that cholesterol is a precursor to vitamin D. We'll get to the vitamin D piece in just a second. Cholesterol is a precursor to lots of other steroid hormones. Later in the semester, when we do a brief dive into endocrinology, we'll talk about some of these hormones. Cholesterol is precursors are necessary to produce coenzyme Q10, which is important for healthy mitochondrial function. Cholesterol is an important component of your lipid bilayer. And we talked about the only way to get rid of cholesterol is you make it into bile acids and you secrete it into your digestive tract. But this is also an indication that that's why we need cholesterol, is we need to be able to make bile acids. So that gets us through statins, vitamins D3 and K2 and their impact on calcium levels. That was this slide. So I want you to know the importance of maintaining proper calcium levels. Again, if you have too elevated of calcium in your bloodstream, you're going to end up depositing it in soft tissues. It's going to lead to things like kidney stones. It's going to harden plaques that are found anywhere in your body, right? So having too low of a calcium can be problematic. We really didn't talk about this. If you are hypocalcemic, that can have definite impacts in terms of what we see calcium being important for, whether it's a secondary messenger, necessary for muscle contraction, enzyme function, bone and teeth formation. So obviously, if you're not getting sufficient calcium into your bones and your teeth, you're not creating strong bones and teeth. So that's why you need calcium. But in order to facilitate getting calcium from your diet where it needs to be, you need vitamin D3 and K2. You only need D3 to get it out of your intestines, but if you don't also have K2, you're going to build it up in your blood and not be able to get it out and deposit it where you need it. So again, excess calcium, because you have a K2 deficiency, can lead to hypercalcemia. And again, that's going to lead to those soft tissue calcifications. Let's see. We already sort of went through this, understand by name and with examples, different transport mechanisms, symport, antiport, uniport, non-mediated facilitated views, and primary and secondary active transport. And then here's the transporters that we sort of went through. We talked about 2,4-dinitrophenol. Be able to draw the structure of 2,4-dinitrophenol. Understand why it has that pKa shift. We went through that pretty extensively in class. And again, its purpose is it's going to discharge a proton gradient. So again, going over here. Oh, I guess I have it over here. Let's see. That was this guy, right? One thing I didn't mention in class, and I don't believe this is something you'd need to know for your test anyways, but I do want you to understand that 2,4-dinitrophenol is what we call an uncoupler. It takes a normal process which couples the energy value in food with the energy value in ATP production, and it connects them, right? But the idea is we have an alternative path. Rather than using that proton gradient to synthesize ATP, that proton gradient is going to be used to generate heat. And in the context of 2,4-dinitrophenol, we said that that was a bad thing, right? Because if you generate excess heat, that can actually be fatal. But here's where it's a good thing. And that's where this purple or this pink piece is that I know is not on your slide because I didn't get a chance to write it down when we finished this story on 2,4-dinitrophenol. UCPs stand for uncoupling proteins. We'll get to those a lot next semester when we talk about metabolism. But maybe you've heard about in either anatomy or physiology, there's different types of adipose tissue. There's white fat and there's brown fat. Give me a thumbs up if that's something you've talked about in other classes. Connor says yes. Nobody else? Okay. Where was it, Connor? Was it in physio?
Yeah, I was in phys.
Yeah. So do you, I'm just curious what level, if you remember, if you don't, that's okay. Do you know why brown fat is called brown fat? What it's very rich in that makes it actually brown in color?
Honestly, I forget.
That's okay. It's very rich in mitochondria. So it's mitochondrial rich. So it actually will do a lot of electron transport. Brown fat is very enriched in infants and hibernating animals because it actually, being very rich in mitochondria, does a lot of electron transport to generate a proton gradient, but it uses uncoupling proteins to take this proton gradient and not make it into biological money. It actually uses these proteins as a channel to dissipate the proton gradient and uses it to generate heat. So when you talk about what we call non-shivering thermogenesis, normally when your body shivers, it's your body's attempt to try to warm up. But for an animal that's hibernating or for infants that have very little body mass, brown fat is what allows them to maintain body temperature. Maintain body temperature when they're not moving if you're a hibernating animal, or maintain body temperature if you don't have a very large body mass, like an infant. So brown fat is actually really important for using uncoupling proteins as a way to generate heat. So we'll revisit that a couple of times next semester, but that's why I sort of have a little plug for it here, just to highlight that it does the same sort of thing that 2,4-dinitrophenol does, but it does it in a natural, intended way. So that's 2,4-dinitrophenol. Again, I just mentioned the uncoupling proteins. We've talked about just isozymes a little bit here, know the locations of GLUT4 and GLUT2 isozymes. Again, the relative Km values. You don't need to know exact numbers, but I want you to know that GLUT4 is going to be less than that magic number of 5 millimolar, and then GLUT2 is going to be much greater than 5 millimolar. Okay, so you don't need to remember those exact numbers, but I want you to know where they fall on that set point for glucose homeostasis of 5 millimolar. Explain the thermodynamic driving potential of concentration gradients. That's this fun slide, right? And again, I don't have videos out here for you to review and watch this yet. Hopefully I will be able to get to those, if not tomorrow, probably more likely to be Friday. But it's all about this equation that we learned about in Learning Unit 1, right? Thermodynamic driving force is directly proportional to the extent of our equilibrium constant, which is the extent of the difference in concentrations of species inside and outside, right? So we have two parts to delta G. We've got a magnitude, what's the actual numerical value, and we have a sign. If we have something that's a positive delta G, we're going to need to put energy in to create that gradient or that concentration difference that we're talking about. If it's a negative delta G, that means we're moving things in a direction to dissipate the gradient. And I like to use a lot of toy analogies. We talked about a slingshot, right? If I just pull my slingshot back a little bit, that's the magnitude of delta G is not very large. The stronger I pull back on that rubber band of my slingshot, the larger the magnitude of delta G is. So that's all I mean sort of about that thermodynamic driving potential. Oh, the last thing is just highlight, you don't need to know this equation, but understand that we have an extra contributor to the magnitude of delta G when we have a species that also has a charge. If we can build up a charge gradient in addition to just a concentration gradient, that's going to be sort of like an extra bonus that we get to our thermodynamic driving force. We already talked about this, uncoupling fuel oxidation and ATP production to generate heat. 2,4-dinitrophenol does that. So does uncoupling proteins. And then we talked about sort of structurally how we have that enthalpic compensation that drives how the potassium channel works. So we did get to this guy today, right? We talked about sort of how the structure of this channel is created such that, and please don't write about basketballs and baseballs if you have to answer a question on this. It's meant to be a conceptual tool to have you understand. Use the names of the species. Hydrated potassium ions, hydrated sodium ions, dehydrated potassium ions. And again, there's an enthalpic cost to doing that hydration, dehydration, and so forth. So we did just talk about that one this morning. So hopefully that one's pretty fresh in your brain. Quick questions on anything before we move on?
Okay, I do have a question on the dinitrophenol.
Mhm.
It has to do with the picture. So I know that it's diet pills. Is
Mhm.
the red thing in the picture dinitrophenol, or is that just what it blocks off? Does that
Oh,
make sense?
so this thing right here, I don't know if you can see the
Yes.
cursor. That is representing a generic carrier ionophore. So this is not
Okay.
specifically, so what it is really representing something like dinitrophenol, or I could actually say it also represents generically how valinomycin works. It's a
Okay.
molecule that actually will transit back and forth through the lipid bilayer. Now, you can actually have a protein that serves this function that never actually dissipates from the lipid bilayer. So maybe this picture isn't the best picture because it's too generic, because whether you're talking about 2,4-dinitrophenol or you're talking about valinomycin, to make the analogy with this picture, I would have these red things actually leaving the lipid bilayer because they will actually transit the entirety of the lipid bilayer to go from the inside to the outside. Does that sort of help?
Yes, I was just because in my notes it made it. I guess I had to draw the picture and I made it seem like that was the dinitrophenol, and then I was like, but that doesn't make any sense. Okay.
So conceptually, it is a carrier. We call it a carrier ionophore because it binds ions and moves them across and dissipates ion gradients. So both 2,4-dinitrophenol and valinomycin are classified as carrier ionophores, but they're not proteins.
Okay. Perfect.
Any other questions before I sort of go on to the last couple of pieces here? And then I'll sort of go through briefly. I'll just flip through homework, see if there's anything in either homework or slides that I sort of didn't touch on yet. There was more than one person that missed this on the last test. So please do make sure you understand the pancreatic hormone that's released for low blood sugar, okay, is glucagon, and it's secreted from alpha cells, okay? The pancreatic hormone that's secreted for high blood sugar is insulin, and it's released from beta cells. So I do want you to know those pieces. I do want you to know that we also talked about the adrenal hormone that's released in response to stress. You can either call it epinephrine or norepinephrine. Both we'll get to when we take a little bit of a scrape the surface on endocrinology. We'll talk about the difference in terms of how those act. We'll look more next semester when we talk about the difference between beta and alpha adrenergic receptors, but we won't get to that till next semester. But epinephrine or norepinephrine, that's the adrenal hormone, and the effects on liver or skeletal muscle and blood glucose. So that is this slide. If you want to put a big star by this slide, this is a really important slide to understand. This one and this one. These are sort of big picture story slides. You are likely to see questions related to these two slides in the later section of your exam, asking you to sort of think about these cascading events, asking you to sort of draw me a start with this signal and end with the response. So I'll sort of talk about those when we look at the homework questions in a second. But I would star these two slides if you need to, if you're looking back at them and you're like, I don't remember what this slide was about, especially these two. There are videos that you can sort of watch to refresh your brain on them. So that is the glucose or the glucagon and glycogen piece. Then there's the normal insulin response versus insulin resistance. The discussion of why insulin is a detox hormone, right? Insulin is an important signal that allows your skeletal muscle, and importantly, I'm just going to highlight here, we showed this on this slide when we went through just a minute ago and talked about glucose transporters, right? GLUT4 is present on adipose tissue. Your adipose tissue is insulin sensitive. You will pull in glucose to adipose tissue when you have elevated insulin levels or elevated blood sugar levels. And that's really important because having high blood sugar is toxic. And we want to make sure that you're not having too high of a blood sugar level. We've actually talked about some of these pieces. So this is sort of the function piece. I've mentioned a lot of this already as we sort of talked about the structure, because it's hard to talk about structure and not talk about function. So we did sort of talk about how the diet pill works, how uncoupling proteins work similarly, again, ultimately negating calorie content from food by generation of heat, right? First law of thermodynamics reminds us that we can't gain or lose energy. Really, we just convert it into energy is not created or destroyed. It's just converted into alternative forms. And again, we went through this already. When we talked about structure, it's hard to not incorporate the function piece with it. And I'm happy to go through things again if anybody wants. I know there's already a video out there on the potassium channel, but describe how the potassium channel operates, why it can be selective over sodium, that smaller ion. And again, just tonight we went over the two glucose transporters and how they operate, how you find them. There were some structural pieces that were sort of up here when we talk about GLUT2 and GLUT4, know their locations, and then again, relative Km values. So I'll pause there for a second before we go through and talk about the last two application pieces. All right, we'll be able to sort of revisit these two applications when we do our case study on Friday. Again, just tonight, we watched the video on how the sodium glucose transport system operates. It's a great system to sort of tie everything together because you have pretty much all three types of transporters in terms of uniport, symport, antiport. It has all kinds of primary active, secondary active, and then facilitated diffusion. Those are the three main types of transport. So it's just a beautiful system to sort of learn about all three of those things together. So we sort of already went through that. We used the story to sort of talk about why diet Gatorade is sort of a fallacy. It is not, you cannot have diet Gatorade be an electrolyte replacement solution. Cannot happen. But if you just want a drink that tastes nice and you want to hydrate and not do any electrolyte replacement, diet Gatorade is fine. And again, I'm going to not mention too much about this right now. You are not going to see much on your exam that has to do with our cholera case study. But big picture, and I sort of said this at the very end of that video when I was sort of talking about things. I know I talked to Connor and Allie about it today because this is some of their stuff that they're going to talk about on Friday for their case study. When you have the cholera toxin bind to a receptor on your intestinal epithelial cells, you essentially go through a cascade of events that ultimately leads to chloride ions being pumped out into your intestinal lumen. And I just wanted those of you who haven't taken sort of anatomy or physiology, sort of talk about this lumen is sort of an outside space. That's what that word means, is lumen is an outside space. And your intestinal lumen is really the outside environment, because when I put something in my mouth, until something comes out my backside, right, you never encounter the inside environment. It is a gut tube. It's a tube within a tube. So that is the outside environment in that intestinal lumen. So what happens with this CFTR, and this is a cystic fibrosis sort of transporter. That's but you have it in other places other than your lungs. You have it in lots of epithelial cells that face the outside environment. And again, we'll talk about this more, but to give you a little context as we're talking about things here, what happens is you have this efflux of chloride ions from this chloride, the cystic fibrosis transporter, and it throws chloride ions out into your intestinal lumen, and that creates essentially an electrolyte imbalance that your body tries to fix by throwing water out there at the same time. And so that's what causes the diarrhea, is because you are dumping all of this water into your gut tube, and that's just going to cause diarrhea. So I know Connor and Allie are going to talk a little bit about, well, how would you want to treat this? And how do you treat somebody who has cholera? What are the things that you want to do, don't want to do, can't do in order to sort of keep them comfortable and help them sort of recover? So that's going to be sort of the last little piece that we'll talk about. So I don't have any slides here to sort of talk about that. But quick questions before I sort of flip through notes, see if there was anything, notes and homework, see if there was anything that I didn't touch on that I want to make sure to talk about. All right, so flipping through notes, I'm just going to quick see if there's any slide that has something on it that we didn't already address. And if somebody sees a slide as I'm flipping through here and you're like, oh, yeah, I have a question on that, you can sort of reach out.
Are we gonna have to know the iodine piece with
No.
starch? Okay.
Now, I'd hope that you remember that if you want to know if starch is in something, you add iodine to it. But other than that, this was just an application of structure affords function. Obviously, I still would want you to remember that starch with its alpha 1,4 linkage is different and generates a coiled shape, and that's different from cellulose, which has more of a sheet shape. That's the thing that I want you to remember from here. And we see that a little bit further. Like we need to know that starch is a coiled shape, because when we talk about how we get starch into bacteria so that they can eat, that coiled shape is important. We just talked about that today in class. You do not need the stuff on artificial sweeteners, and you'll notice there was nothing in there in the study guide. That was more just like, hey, this is like a cool application of stuff that you know. One of the things that I sort of mentioned when we had one of those observers in class that day was, hey, I really hope you guys gain a new appreciation and then understanding of what the backside of your food products are. Like, get away from the front side, which is marketing. The backside is the truth, the reality that they hope nobody oftentimes can like understand or read. But you guys are going to know a lot after this class in terms of being able to look at and understand what's in your food products. So yeah, nothing here that you need to know. I do want you to know a little bit with blood groups. It's carbohydrates on the cell surface. I do want you to know what the 4 blood types are. This is probably something you learned in, elementary school or high school, so it's not challenging. But things like, okay, which is the universal donor, which is the universal acceptor, and maybe even if that was the simplest level that you got to, like in, high school or middle school, you now know a little bit more because it also allows us to think about this concept of antigen, antibody, and so forth. So I want you to understand it just a little bit deeper in terms of understanding why somebody who's type O can be the universal donor, but why somebody who's type AB could be the universal acceptor. It has to do with the antigens that are on their own cells and the antibodies that are present or not in their blood. Don't worry too much about the Rh factor, whether that's plus or minus, but understand the AB, A, B, AB, and O blood types. All right, so that's it for Unit 5 notes. Let me go. I was just looking this stuff up, so was just going to look at the homework for Unit 5. I hadn't opened it yet. Let's see. Structures. I'm just seeing if there's anything that we sort of didn't talk about already. Little math. I would hope that you guys could do this math, right? You guys know I don't do a ton of math, but sometimes when it has relevance, right? Be able to show the connection between 5 millimolar glucose and 90 milligrams per deciliter. And again, insulin response. We have those slides, which there's videos on. This is just, and again, oftentimes your homework is just meant to be a way to allow you to summarize your notes in a different way. So again, these are sucrose, lactose. We didn't talk about maltose, so don't worry too much about that. But everything else we talked about, again, know the monomer, know the linkage, whether it's fiber or fuel, whether it's a reducing or non-reducing sugar. The only time you're going to have a non-reducing sugar is when you have head-to-head linkage. And the only one we talked about was sucrose. And if there's a usage or a context that we talked about it in, again, the only one we really didn't talk about was maltose. Let's see. Yeah, I think we've talked about everything that was there. So before I move on from Unit 5 and quickly look at 6, any questions on anything from 5? All right, here's our notes from 6. I think we went through most everything. Let me see if there's anything I didn't talk about. Again, structure affords function. Understand that cis double bond puts a kink in. are fatty acids, so that is going to affect intermolecular forces. That's why things that we call saturated fats are fats and solids at room temperature, whereas the omega 3 and omega 6 fatty acids or fats really are going to be found in oils at room temperature. A little bit of stories about things, right? We didn't talk too much about this on the study guide or homework questions yet. I do want you to know that the purpose of hydrogenation is to convert unsaturated double bonds into saturated single bonds, right? And unfortunately, what can happen in that process is sometimes you actually do get rid of the double bond and you generate a saturated fat, and sometimes you just isomerize it. And that's how we get to trans fats. Trans fats are structurally similar to saturated fats in terms of how they behave, right? But we have a hard time. We'll look more deeply at this next semester, understanding why trans fats have a negative impact sort of on your cardiovascular health. Plant fats are cheaper, animal fats are more expensive. Partial hydrogenation was a way to try to take an inexpensive oil and have it have the palatability of a fat. So that's all that was really on those stories. I think Allie actually asked a question one day in class about this. She's like, so what do we need to know about this? And I sort of said with this slide, it's really the top part. I do want you to know the difference between the terms necessary and essential. There's lots of things that are necessary in our body. Glucose is necessary, but glucose is not essential because we can make it ourselves. So know the difference between those two terms. Identifying omega-3 or omega-6 fats, knowing that omega-3s are anti-inflammatory, omega-6 are pro-inflammatory. You do not need to know these names like ALA, EPA, and DHA. Don't need to know those. But I do want you to know that particularly the omega-6 fats, and we have that sort of on one of our last slides, are responsible for doing a lot of the synthesis of prostaglandins, which are responsible for pain, inflammation, and fever. So again, those omega-6 fatty acids sort of are able to do that. So that's that slide. We talked about ketone bodies already. You don't really need to know much about like MCT or coconut oil. It used to be that, and maybe it's just not on the market as much, but I'd had a lot of questions at one point that, people would be like, oh, I hear I put MCT oil in my coffee. It's supposed to be like a great way to like have ketone bodies in the morning. And so we had sort of talked a little bit more about that. Concepts of prebiotics and probiotics. I do want you to know the differences between those terms as they relate to microbiome health. This is the theme we're going to move on to when we do our enzyme sort of learning unit here, enzyme catalysis. Condensation is how we make linkages. Hydrolysis by adding water is how we break linkages. So every enzyme we're going to learn about when we start learning about enzyme catalysis is going to be a hydrolysis enzyme. So an enzyme that breaks a linkage. And every once in a while, I continue to throw in some of these big picture topics here, like, oh, hey, excess glucose is toxic. Here's what your body does when you have high insulin. Again, you're going to pull in and synthesize. You can do it in your liver. You can also do it in adipose tissue. But again, lots of triglyceride synthesis happens in your liver. Your liver is going to offload those triglycerides into your storage bank, your adipose tissue, right? We talked about your adipose tissue like being a bank, that you need insulin in order to make fats and sort of deposit into the bank. But if you don't have your insulin levels fall, if you are insulin resistant, you can't make any withdrawals from that bank. And that's a big picture thing that we're going to continue to revisit throughout the course here. Let's see what else here in lipids. We talked about sort of the structures that these molecules can make. This is sort of a unique class of molecules because we have hydrophobicity we need to think about. Now, we did talk about hydrophobicity a little bit when we talked about, those 9 amino acids that are technically classified as nonpolar. But we sort of reconciled those by saying, oh, when we fold a protein, they just go in the center. So we don't need to worry too much about them. But when we have fatty acids, phospholipids, or triglycerides, we've got a giant fatty portion that we need to think about what we do. And so the shape of these molecules is going to determine sort of their macromolecular structure, either with soap molecules to make micelles, with phospholipids to make lipid bilayers, or triglycerides literally just get packed on the inside of some of these lipoproteins. And again, we already went through the next couple of slides here, sort of talking about cholesterol. I think we mentioned a lot of this. It's kind of revisited on the second slide. Big picture, cholesterol is not good or bad. It's an organic molecule that has lots of functions. What it is transported with and whether you are in a state of inflammation has a lot to do with whether or not people have cholesterol issues. Talked about that slide, talked about the statin dilemma. We talked about that. This was the last little piece. I do want you to know the name of this enzyme. Another enzyme, like I want you to know HMG. And a lot of times these enzymes are ones that they have a drug connection to, which is why I want you to know them, especially in Biochem 1 here. So I do want you to know about the enzyme that we call cyclooxygenase, or COX. You don't need to remember PGH2 synthase, but I do want you to remember COX, cyclooxygenase. This is an enzyme that's responsible for doing the conversion of, for example, this omega-6 fatty acid into a molecule that's going to produce pain, inflammation, and fever. Okay, it produces those prostaglandins. Lots of different drug molecules will inhibit COX. Now, what's interesting about COX is there's different isoforms of COX, right? There's an isoform that's responsible for protecting the stomach lining. Well, if you have a drug that inhibits that enzyme, then that drug by proxy is going to generate stomach issues. So that's sort of what's problematic for things like aspirin, ibuprofen, naproxen, right? You got stomach irritation issues. Acetaminophen is great because it only inhibits COX-2, but the problem is it's only COX-2 in the central nervous system. So you don't have any anti-inflammatory properties of things like acetaminophen, which again is Tylenol. And so talking, and I know I said at the very last part of the video that I made earlier in the week, I talked about Vioxx and Celebrex, which are selective COX-2 inhibitors. So they don't have those peptic ulcer pieces, but they seem to have negative cardiovascular implications. You don't need to remember that, but that's why you don't see a lot of those selective COX-2 inhibitors on the market anymore. All right, so that was the end of notes. Let me take a quick glance at homework. The homework, if I'm remembering correctly, was pretty simple. I think it was just a single page. This is a student from a previous year, so I think everything is right here. This is what I was sort of talking about. Like this student actually did draw their fatty acids like in that sort of cis configuration, but it's okay if you draw it just as a zigzag and then label like, hey, I know this is cis, but it's a pain in the butt to draw. This homework has more detail than you need to know. Like there's some of these things that you know, like I even put like that there was blanks or like you didn't have to know, but oh, and you definitely don't need to know these names. So don't worry about that. I had it. It may not even be part of your homework anymore, but you do not need to know these names. But yeah, the difference between whether you have ApoA1 or ApoB100, again, noting here that a key protein that you have in the small dense LDL particle is ApoA. Yeah, so that's it for that. And let me look at the homework key. I think it was a pretty straightforward. It was just a single page homework key for Unit 7. We already talked about sort of this equation, summarizing the types of transport or differences between GLUT2 and GLUT4. And then there's the story with our sodium glucose transport system. So not a lot of homework there. And I will actually take and circulate out to you guys. I'll do it when I post the link. So I'm going to post 3 things tonight. I will post, and it sometimes takes like an hour for them to process and get me a link for the Zoom session. So I won't put this right away because I want to have all 3 of these together. I'll have the link for the Zoom session. I will have my notes from Unit 7 that I will send out to you guys, particularly with this last 2 slides. And then I also will circulate that sort of topic headings for the exams, so you sort of know what the exam is going to look like, in terms of those topic heading pieces. So thanks for sticking around. I know this was longer than I wanted to be, but I wanted to be able to get through those couple of slides that I hadn't been able to finish in class. So I'm going to pause there for a second, see if anybody has any questions. I will stick around. If anybody does have questions, we can sort of go over things, but that's all I sort of have for tonight. Or if there's anything that anybody wants me to go back to. All right. I will stick around. I always wait around till the last. It's like, no, you hang up. No, you hang up. I don't hang up until the last person hangs up, just in case somebody sticks around because they have a question. Do tell me though if that happens and we're having a conversation that should not be recorded and available for everybody else. But I'll stick around if anybody has any questions. Otherwise, the formal sort of review session is done, and I will see you guys tomorrow in lab. Reminder, early morning crew, Maria. I don't know if Madison. Yep, there's Madison. 8 o'clock. I have to be in at 7 to start the FPLC, but you guys don't need to be there till 8. So you guys are going to be in there right as it's ending. And then we'll be able to do sort of our analysis. It's kind of a pretty low key lab. It's kind of fun. We'll have a chance to sort of talk about and see how a lot of things work. So regularly scheduled lab tomorrow. All right, I'm done. Bye, Connor.
Have a good night.
Oh, Charlotte. I think she heard like somebody, like a doorbell or something from. Oh, no, you heard Daddy. That's the garage door opener. Go find Daddy.
Okay, bye.
Have a good night.
All right. Bye, guys.
Why do I leave? The leave button.
I don't see it. Oh,
Right
why is
there.
it the different?